This lecture is going to talk about how the ideas from Boolean algebra can be used with logic circuits. With computers, all information is stored as binary numbers, that is base 2, either 0 or 1. For instance, this string of zeros and ones is often used to represent the letter C on computers. Each one of these zeros and ones is called a bit, and the list of zeros and ones is called a string. Zeros and ones work well with computers because we can talk about zeros and ones in terms of voltages. That is, for a 0 you'd have one voltage level, and for a 1 you'd have another voltage level. Devices can be made to combine two different strings of numbers to represent something else. These are in general called arithmetic logic units, or ALUs. These ALUs are built with what are called logic gates, and we're going to talk about just some of the simple logic gates. The first one we're going to talk about is the AND gate. This is how an AND gate is represented graphically. We have two inputs A and B, and they are ANDed together to give an output of A and B. Let's look at what the output would be. This should be really familiar because this is basically our truth tables. So if we have A and B, if we have 0, 0, that would be a 0, and then 0, 1 would be a 0, a 1, 0 would be a 0, and only the case of 1, 1 would give us an output of 1. I'm using 1 for true and 0 for false. So notice this AND gate has the same truth table as we had when we were talking about AND. And I've quickly put up the truth table for our AND operator. And you can see it's exactly the same. The next thing we're going to look at is an OR gate. This is the graphical representation of an OR gate, again with inputs A, B, and the output of A or B. And this is our truth table for the OR gate. Again, remember, unlike in English, if both A and B are true, then A or B is still true. The next gate we have is the NOT gate, or the inverter. It takes an input of A and gives an output of A complement. And there's our truth table for the NOT gate. From these building blocks we can build more complicated systems. Let's look at this circuit for instance. We have an input of A and B, and a NOT gate, an AND gate, and an OR gate. Notice at the point where A goes two different directions, there's a larger dot there. You need to specifically write that larger dot to make sure that you're showing that the signal is going two different places, and it's not merely a crossover from one wire to another. So how would we find the output of this system? Well, we're going to build a truth table again. Let's first look at this stage. This stage, we'd have A complement. So let's write what A complement is. At the next point, we have A complement or B. So we're ORing these two columns. Finally, our output is going to be A ANDed with A complement or B. So I'll be ANDing these two columns. And that's the output of this system. What's interesting is this is exactly the same truth table that we got for a simple AND gate. And when you have two truth tables that are identical, and let me go ahead and write the AND gate truth table, if these are the same, then these are equivalent circuits. Take this example and see if you can go ahead and build the truth table for this one. Pause the video to work on this yourself. Here's the solution to the practice problem. Our first point would be to look at the point A and B. Then we would determine A complement, and then we would have A complement ORed with A and B. You might guess that we can do some simplification of circuits. Remember, equivalent circuits have the same truth table output. And we're going to talk about two circuits being equivalent with the equal sign. To be able to simplify circuits, what we want to do is prove that these four properties hold: the commutative property, the distributive property, the identity property, and the negation property. Let's look at this one and show how we would prove this. We'd want to build a truth table for the left-hand side and then build a truth table for the right-hand side and show that they are in fact equivalent. I would first look at B times C, looking at these two columns to determine this one. And then I'm going to take A and OR it with the results of this column. Now I'm going to do the exact same thing to the right-hand side and compare my outputs. I first look at A or B, then I look at A or C, and now I AND those two together. And I see that the outputs of both the left-hand side and the right-hand side are identical, therefore the left-hand side is equivalent to the right-hand side. So I've just proven the distributive property. I'm not going to go through all the other properties, but these are the types of things that could easily be asked on an exam. And we're now just going to assume those four properties hold. That is, the commutative, distributive, identity, and negation properties. If we went back to our first example, we should not be shocked that that is in fact equal to an AND gate, because we could use the same properties that we've been using before, but now it's in terms of circuitry. I'd first do the distributive property, then I would use negation, then I'd use the commutative property, and again this is a really easy step to forget, and now we'll use the identity property to get down to A and B. I'm going to remind you that we don't have to use the dots to talk about our ANDs. We can just leave that symbol out, and if we see AB, we'll remember that's the same thing as A and B. Let's look at this circuit. If we took this circuit and the question was, how could we simplify this? What we would do is rewrite this as a Boolean algebra expression. So let's look at this point first, and that bit would be equivalent to A plus B. At this point, we would have A complement. At this point, we would have A complement ANDed with C. At this point, we would have A complement ANDed with C, and all of that complemented. And then finally, we would have A or B ANDed with A complement C, all complemented. So from here, I'm going to see if I can simplify this at all. The first thing I'm going to do is use De Morgan's law to clean up the right-hand side of this. I'll have A complement complement. I'll use another property called the double negative property to rewrite this as simply A plus C complement. And now I'm going to use the distributive property in reverse to factor out that A. And now I have the circuit simplified down to A or B and C complement. Why would I want to do this? Well, up above I have a total of 5 gates. I have 2 inverters, 2 AND gates, and 1 OR gate. Down here, however, I would have just 3 gates. I would have a negation, I would have an AND, and I would have an OR gate. So if you can take a circuit and simplify it mathematically and decrease the number of gates, you've done 2 things. You've decreased the complexity of the circuit, and since I have fewer gates, you've also decreased the cost of the circuit. Go ahead on your own, pause the video again, see if you can come up with, first of all, the Boolean expression for this, and then how to simplify it. And this is a good example of showing why we need to put dark spots on the graph where we want to show where the signal is going. Notice this area here, that is just 2 wires crossing, but the signal doesn't cross. That's sort of like if we had insulated wires. So if you want to show that the signal is actually moving through a circuit, make sure you put at all intersections a large dot. And just like before, we would find what we have at all the different points until we came up with a final output. And now we would take that final output and simplify it. And these are the steps we'd use to simplify. De Morgan, double negative, distributive, the commutative property, negation, the universal bound, and then finally the identity property. And so that crazy circuit just simplifies down to simply the input A. Finally, we're going to talk about how we can go from a truth table to a circuit. The circuit we will come up with this method might not be the simplest circuit, but it will give us the truth table that we're looking for. Let's look at an example. Say this was our desired output given these three inputs. What we can do is look at all the cases where the output is equal to 1 and see what causes that output to be 1. For this line, A is 0, B is 1, and C is 0. We could write that as A complement, B, C complement. Likewise, A, B complement, C complement, A, B complement, C, A, B, C complement, and finally A, B, C. These are all ANDed together. The A complement, B, C complement are all ANDed together. However, all of these 5, any one of those would make this true. So these we want to join together with ORs. If I put this all together, a circuit that followed this would be equivalent to the truth table output I'm looking for. Rather than have one source of A, I'm going to write A 5 times, B 5 times, and C 5 times, understanding that the value for A is the same for all the A's. And if I wanted to look at this first AND gate, I could have all 3 inputs going in. Now notice what I've done. Instead of putting an inverter in, I've put a circle right by the input to the AND gate. So this is the same thing as an inverter. It's just a shorthand method of drawing this. That would be my second case, that would be my third AND gate, and my fourth and fifth one. This could go into a giant OR gate, and this is one way that truth table could be generated. We could go through and take this huge expression and simplifying it. It's a little bit tedious, and I'm going to just tell you what the final answer would be. I could simplify all of this down to simply A or B and C complement. And it would be pretty easy to check this. If I went ahead and found the truth table for A or B and C complement, you can see that that matches the original goal that I had. So they are in fact equivalent circuits. But simplifying this down to this is more complicated than I'd expect you to do on an exam.